Okay, so let's talk about how to find a center of mass for a lamina that has a density function that's not necessarily constant. So in the previous video, we sort of ended talking about moments of masses concentrated at points and the moment of a system of a finite number of masses, which we talked about with this little diagram right here. So again, the idea is that the moment of an entire system about an axis is the sum of all of the moments of each individual mass at each one of those points. So going back to here, if I looked at this lamina and I wanted to find the center of mass for this lamina, not the center of mass, we'll get to that. If I wanted to talk about the moment of this entire lamina as a system of point masses about either the x or the y-axis, what I could do is approximate that by selecting a finite number of points within this lamina. And the way that I could select those points is divide this rectangle up like we did before in all these sub-rectangles, and then choose one point within each one of those sub-rectangles. And we showed before that gives us an approximation, or we can approximate the mass of any one of those points by using a small subrectangle containing it. So that's kind of what we're talking about right here. If we divide that lamina up into a bunch of subrectangles and select a point xij star, yij star in each one of those, we showed on the previous page that the mass of that little rectangle is approximately the density at that point times delta A. Okay, and again, the idea there is that the density will vary, even if this is a continuous function, this will vary very little within that small rectangle. So this approximates the mass of the rectangle, and we can think of that as the moment of the subrectangle Rij relative to the x-axis, if we multiply by its distance to the x-axis, which again would be given by the y-coordinate of this point, yij star. So this gives us an approximation to the moment of this subrectangle relative to the x-axis. Then if I add up the moments for each of those subrectangles, that would give me an approximation to the moment of the entire lamina about the x-axis. That's what this double sum represents here. Okay, so notice at this point we're using a finite number of these subrectangles to approximate that. But if I were to take a limit as m and n go to infinity, we would expect that approximation to become accurate. And then of course, because that's set up like a Riemann integral, a double Riemann sum, that limit should turn into a double integral here. Notice now that the yij star becomes a y here. So the moment of the lamina d about my x-axis is the double integral over d of y rho xy dA. Sometimes people get a little confused here because they see a subscript of an x, but then there's a y showing up here. And remember, the reason for that is because that y represents the distance from any given point in our lamina with y as its y coordinate from the x-axis. We have a similar derivation here. The moment of the lamina d about the y-axis looks similar, but with an x here instead of a y. Okay, going back to calculus 2. The way that we defined the center of mass was we took each of those moments, the moment about the y and the moment about the x-axis, divide them by the total mass of the lamina, and that gives us x bar and y bar. Together, x bar, y bar gives us the point representing the center of mass. And you talk about why this little formula looks the way that it does in calculus 2, so we're not going to talk about it again here. But notice that actually gives you 3 integrals that you need to evaluate. One for the moment about y, one for the moment about x, and then one for the mass of the lamina. They look similar, but each one is a different integral. This little diagram shows what the center of mass is, and again, this should be something you're familiar with, but the center of mass of a two-dimensional lamina like this represents the point at which I could place a fulcrum such that this lamina would balance if placed there. Okay, so we're going to do one example of calculating a center of mass. And for this one, we're looking at a lamina that consists of two semicircles given by these two functions here, as well as the portions of the x-axis that join them together. We'll sketch that in a second so you can see what it looks like. We want to find the center of mass of the lamina if the density at any point is inversely proportional to its distance from the origin. This is kind of typical of these problems where the description of our density function is not actually an explicit function that we're given. It's given to us in terms of some kind of proportionality relationship. So the first thing I want to do before we come up with what that density function should look like is I'd like to sketch the region, sketch the lamina D. So it's two semicircles centered at the origin, one with a radius of 1, one with a radius of 2. So I get this kind of a semicircular annulus type thing. That's not really what I want to call that, but like half of an annulus. Okay, so this is the region D that we're going to use here. And when it says together with the portions of the x-axis that join those two semicircles, it's talking about these portions right here. Again, because this is kind of a circular shape, it's definitely going to be an example that I want to use polar coordinates for as opposed to rectangular coordinates. It's far, far simpler if we do this in polar coordinates. So we have a few things that we need to find. We need m, so the mass of this lamina. We need the moments with respect to the x and the y, and then we can use all of those to get our center of mass. But I can't do anything unless I know what my density function is. So we need to find rho of xy. Okay, rho of xy. So the description of this function says that the density of any point in this lamina is inversely proportional to its distance from the origin. That means it's equal to k over an expression. K is some unknown constant here. We call that a constant of proportionality. It's k over some expression that represents the distance between the point xy and the origin. Well, we know that that would be given by the square root of x squared plus y squared. That's our density function right there. Okay. However, again, if we're going to convert this to polar coordinates, this will look a lot nicer in polar coordinates. Let's start by setting up an integral to solve for m. So m, the total mass of my lamina, is going to be given by the double integral over d of our density function, dA. Okay, now this density function, I want to convert it into polar coordinates. In polar coordinates, it's going to look like k over, remember, x squared plus y squared gets converted to r squared. The square root of that would just be r. That's much simpler looking. So I can write this as actually, before we do that, let's describe our region in polar coordinates so I know what my limits of integration should look like. D is going to equal the set of all r theta such that, hopefully you've done enough of this by now that you can see where I'm going to get these from. R is between 1 and 2. Theta is between 0 and pi. Not 2 pi, but just pi for this example. Okay, so that gives me limits of integration to use. For for theta, 0 to pi. For r, 1 to 2. And then the function that we're integrating, we found up here to be k over r in polar coordinates. And then my dA becomes r dr d theta. Okay? This simplifies by a great deal because the k, the constant of proportionality, can be brought all the way out of my integral. The r's cancel. And what I'm left with, if I take the d theta out here, is the integral from 0 to pi of d theta times the integral from 1 to 2 dr. Okay? each of these will become, the solution to each of these is just the difference between their limits. So this becomes pi, and this becomes 1. So my integral just becomes k times pi times 1, or pi k. See how much better that is with polar coordinates. If you wanna have some fun, try it in rectangular coordinates and just see what that looks like. It's kind of a mess. All right, let's find the other two integrals that we need. Let's start with mx. Remember, mx, the moment about the x-axis, is a double integral over my lambda d of y, rho of xy. And again, remember, y is the distance from any point to the x-axis. That's the reason we use y, dA. Okay, so I already know that the rho xy is going to convert to k over r, like it did here, and my dA is going to convert to r dr d theta. I have the same limits of integration here because I'm using the exact same region. So I already know what's going to happen with most of this. The only thing that's different now, the y in polar coordinates converts to r sine of theta. So I'm going to end up pulling the k that I have out of that integral. Same limits of integration here, 1 to 2. My y is going to become r sine of theta, and then I have my dr d theta there. Okay. All right. I'm going to work vertically here. So let's separate things. I have the k goes from 0 to pi. Let me take the sine of theta, d theta, out to that integral. And here we're going to have from 1 to 2 r dr. Okay? This becomes k times, so if I integrate this, I'm going to get negative cosine of theta from 0 to pi. And then if I integrate this, I'm going to get r squared over 2 from 1 to 2. And this comes out pretty nicely. This comes out to just 3k after everything has been simplified down. All right, so that's fine. Let's look at my now. All right, my. So this one we're looking at a double integral over that region D of this time x times rho of xy dA. Okay. Now, if you think about what happened here, the only difference is that I have an x instead of a y. So that in polar coordinates will look like r cosine of theta. Okay. So that's going to give me this double integral k times the integral from 0 to pi, integral from 1 to 2 of r cosine of theta dr d theta. Okay, so the steps are going to look really similar from here. I'm going to let you fill in the gaps, but if I do the integration here, this one actually comes out to just 0. All right, so that's pretty convenient. Now all that's left for us to do is to use these quantities to get our center of mass. So my center of mass has x coordinate equal to x bar, which we find from doing my over m, which in this case is my is 0, so it doesn't matter what m is, that's just 0. Y bar we find by taking mx and dividing that by m. So mx was not 0, mx gave us 3k. And remember, m was pi k. That gave me 3 pi. Together, those create my center of mass, 0, 3 over pi. Okay? So one thing I want to point out about this one, you notice, first of all, our density function had an unknown constant in it, which is typical because a lot of these problems, again, are defined using some sort of proportional relationship, either directly proportional or inversely proportional in some way. Those always introduce this unknown constant, But the only place where the constant ended up showing up in our answer was here, and it divided out. So that means we never needed to know what k was in the first place. That's why we can get away with doing problems like this. Another thing worth mentioning, if I were to look at where this point is on the lamina itself, 0, 3 over pi, that implies that it's somewhere on the positive y-axis. And that kind of makes sense. I mean, we do have symmetry about the y-axis, so we would expect the center of mass to be somewhere along that axis. You do want to be careful with that intuition, though. In Calculus 2, you can get away with that intuition, and it's because we're assuming the density over that lamina is a constant. But if that density is not constant, depending on what function defines the density at a given point, we may not have those properties of symmetry that we had in Calculus 2. For example, if this lamina, even though it has symmetry about the y-axis, if it was far more dense over here than it is over here, we would expect our center of mass to be over on the left of the y-axis, somewhere in quadrant 2. But in this case, that's not what happened. So you do need to be careful if you're trying to use symmetry to solve these problems. You can't necessarily use it the way you would think. Okay, that's going to be it for us in this section. If you were to read through all of section 15.4, which you do not need to, you would talk about another use of the term moment in physics, moments of inertia, which are second moments. If you've been through physics, you may have talked about that. Moments are a big topic in that discipline. There's also a big section or a big part of 15.4 devoted to probability, the use of double integrals and joint density functions, which is a big thing in probability theory. We're not going to talk about that here, but if you ever do take a course in probability theory, you'll cover that entire topic from scratch. Okay, and that's going to wrap it up for us.